Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is NBC 2020 Response Spectrum Analysis in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of our US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be joining me as your moderator, answering any questions you may have. He's a technical support engineer, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So as far as the content over the next hour today, we will begin with a modal analysis of the structure shown over here on the right-hand side to determine the natural frequencies and mode shapes. We'll then move on to a response spectrum analysis, and in particular, according to the NBC 2020. For both the modal and the response spectrum analysis, we will review the results both in graphical and tabular form. Then we want to introduce our new building model add-on within RFEM 6 that will help organize our results from the response spectrum analysis by stories. And finally, at the end, we will consider the base shear requirements from the NBC 2020 and see how those are related to RFEM 6 and the result output. So before we begin, I want to discuss the NBC 2020 earthquake methods of analysis that are given in Article 4187. So we do have the equivalent static force procedure that is provided in 41811, and this is certainly a simplified approach for seismic design. Now, this can be applied for buildings that are of seismic category SC1 or SC2, given in Table 4185B. It also can be applied to regular structures with a height less than 60 meters and a fundamental lateral period less than 2 seconds. We can also apply this simplified approach for irregular structures, and we would refer to Table 4186 to see what categorizes a structure as irregular. But the height must be less than 20 meters, and that fundamental lateral period must be less than 0.5 seconds. Then we have the dynamic analysis procedure in 41812, and this includes the response spectrum method, the time history method, or the nonlinear dynamic analysis. And this should really be applied to all structures that do not satisfy the simplified requirements set forth in Article 4187. For today, we'll move forward with the response spectrum method for our structure today. So we'll begin in RFEM here, where I have already modeled our multi-level story structure. So we'll quickly go over a bit of the model input as shown over here in the RFEM 6 navigator on the left. So we can see our input materials, and a majority of the structure is defined here as a concrete material with a compressive strength of 40 MPa. But we also have a small steel structure up at the roof level here with a material of A992 steel. As far as our cross sections, you'll notice that our concrete columns that are spanning between floors are just going to be square 350 millimeter by 350 millimeter concrete rectangular sections. And then as far as our steel members, we have several W shapes defined directly from the RFEM 6 CSA library. And finally, we have the thicknesses defined of our surfaces. So this would include our floor slabs here, which are defined with a 300 millimeter thickness. And then we have the thickness of all of our shear walls, which are going to be defined with a slightly smaller thickness of 200 millimeters. So that's just a basic overview of the structure, but we would also like to take a quick look at the applied loading that, again, I've already added to this particular model. So within our dropdown, we have three simple load cases, all gravity loads. The first is going to be our dead load, and this is going to be a surface area load of 3.5 kilonewtons per meter squared applied at every level. We also have a live load. So with a modified magnitude here of of 2 kilonewtons per meter squared, again applied at every floor level. And finally, we have just a general snow level or snow load at the top level here of 1.5 kilonewtons per meter squared. So now that we have reviewed the overall structure and the loading, we want to move forward now with our modal analysis. So we want to right-click on the model name here in the project navigator to visit what's called the base data dialog box. And this dialog box would be presented to you when you first create a new model within RFEM. But on the second tab are all of our optional add-ons. So to quickly explain the configuration of RFEM, the base program itself allows us to fully model the structure, including all of the materials and cross sections from the library. We can apply loads and run a basic static analysis. But the minute we want to move forward with design according to the various standards, we would activate one of these add-ons, for example, concrete design, steel design, timber design, and so on. And in particular, today, we want to activate our dynamic analysis add-ons, and we'll begin with the modal analysis. So on the third tab, we will generate our load combinations automatically according to the NBC 2020, but we see all of the relevant international standards that are available in the base program as well. And because we have activated now that dynamic analysis add-on, we will go ahead and reference the NBC 2020 here. So once we have activated that add-on, we will go back into the program and we want to visit our load cases and combinations dialog box. Well, we can immediately pull that up here by editing the active load case. And again, under the load cases tab, we see those 3 simple load cases that we just reviewed, dead, live, and snow, but we're going to create a 4th load case. And the load case name is going to be modal analysis. Now, because we have activated that add-on, you will notice here that within the dropdown, we now have a new analysis type called modal analysis. And this is only available because we have activated that add-on. So you'll also see a lot of these settings immediately modify in comparison to the static analysis. The first thing to take a look at is a modal analysis settings. So we'll go into the edit dialog box here and we have a couple default options. The first input is the method for determining the number of modes. So this is by default set to user defined, where we can directly put in the number of mode shapes we would like to solve for. And for today, I'm going to increase this to 10, but you can solve for 10, 20, 50, 100 different modes if you prefer. The alternative method in this dropdown is automatic to reach a maximum natural frequency. So you'll notice that we can input in the maximum natural frequency and the program will determine the number of modes needed to reach that particular value. So going back to 10 modes, the second drop down here is going to be the method for solving the eigenvalue problem, and 3 different options, including the default Lenkos solver. And this is really an iterative method to determine the lowest eigenvalues and corresponding mode shapes. It really allows for a quick convergence. The second option is the root of the characteristic polynomial, and this is an analytical solution solved for using a direct method. It's really ideal for small structures for the precise calculation of higher eigenvalues. And finally, we have the subspace iteration. This should be applied to large FE models where only a few eigenvalues are determined in one step. So again, utilizing the Lenkos solver for today. You will see an additional option down here to find modes beyond the frequency. Well, when we have this set to the root of the characteristic polynomial, we can activate this option here to input in a frequency to eliminate local modes where members and surfaces have a low natural frequency. But you'll notice when we change this back to Lenkos, this is not an option to activate. Then moving on to the mass matrix setting. So we have 3 different types, including the diagonal, and this is where masses are going to be lumped at the FE nodes. The second and default option is the consistent mass matrix, where shape functions are used for a more realistic mass distribution rather than necessarily lumped at those FE mesh nodes. And finally, we have the unit mass matrix, and this is where masses at every FE mesh point are set to a value of 1.0. This is certainly a more mathematical approach used for a numerical analysis. So for today, we will take advantage of that default consistent mass matrix. Now, you'll also see that we can consider the masses in the translation directions based on the global X, Y, and Z axes, as well as rotation about X, Y, and Z. When I eventually move forward with my response spectra analysis, I am only considering the orthogonal lateral directions X and Y. Therefore, for my mass matrix, I'm going to deactivate these additional options here to only consider as well in the direction X and Y. And finally, we have our settings tab. So the mass conversion type is set to the Z components of loads by default. This just means that any loads that we have defined in those other load cases like dead load, live load, snow load, whether they are in the vertical direction up or the vertical direction down, they will be converted to masses for this modal analysis. The second option is the Z components of loads in the direction of gravity. So only downward loads will be converted to mass. And finally, the full loads as mass will, despite in which direction we have our loads defined, X, Y, or Z, these will always be converted to masses directly. Down at the bottom, we have the ability to activate an initial pre-stress for members and surfaces of the type cable or membrane. So we don't have any cable or fabric tensile structures for today, but that is an option if you are running a modal analysis on these types of structures. And finally, we have the neglect masses. So the default here is no neglection. We will get into this topic a little bit later on, but for now, I want to consider all masses. So when I click OK, you will notice that I want to import in the masses from either a load case or combination. And within this dropdown, I have access to the load cases dead, live, and snow. But if we refer to the NBC Article 4182, the code actually tells us how we should combine these load cases for a mass combination to be considered with the modal analysis. But we don't exactly see that within the dropdown here. So we must initiate that, and we will jump to the Design Situations tab. Now, by default, the program will automatically create two design situations for ultimate limit state and serviceability according to the NBC. But notice I've deactivated these for now. They're not relevant for our dynamic analysis at the moment. So I'm going to create a third design situation here. But within my dropdown, we now have the ability to set the effective seismic weight. And now that we've created this design situation, what we should see is our mass combination automatically created under the load combinations tab. And we do have that load combination, or what we'll use as a mass combination, defined, but you'll notice that it only includes 100% of the dead load. We don't see any consideration for live or snow load. Well, this is because going back to the load cases tab, that by default under this additional settings for dead load, we'll always consider this within the effective seismic weight. But you can uncheck this option if there's load cases under dead load that you would prefer not to include in that mass combination. However, under live load, these particular load cases are not considered by default. So we just simply need to activate them here to be considered in that effective seismic weight combination. Same concept for snow load here. And now when we jump to the load combinations, we will see all three load cases considered with the relevant factors directly from the NBC. So 100% of the dead, 60% of the live, and 25% of the snow. So jumping back to our load cases and under the modal analysis, we can now use our drop-down box here to select that mass combination. So now these relevant load cases will be converted to mass. Okay, we're now ready to run the calculation, so we can simply hit calculate under this particular load case modal analysis. The program will generate our FE mesh for us, and we are going to calculate a total of 10 different mode shapes. Remember, this is the input that we have input into the particular modal analysis settings. We will also consider the mass conversion of the particular mass combination that we have also set. So when that calculation is done running, we can take a look at our results. And over on the left, we now have a fourth tab available in the navigator. And within our dropdown, we see here 10 different mode shapes that we can actually cycle through to see the response here of the structure. So currently we're viewing the mode shape, and notice at the very bottom here, we have the ability to scale the mode shapes. Now the default option is set here so that the magnitude of the mode shape vector is set to a value of 1.0. That's why we see a max value here of 1.0. But there are some different options we can easily toggle to if we prefer, but most likely we'll be utilizing this first option. So in addition to viewing the mode shape here, you'll also notice the ability to take a look at the masses on the structure used for this modal analysis. And if I zoom in here, we can actually see the mass magnitude at every single FE mesh point that was used in this calculation for our members, our floor slabs, and also our shear walls. So in addition to the graphical output, we certainly want to visit the tabular output here. So once this calculation is complete, we should also see the ability within our dropdown to jump to the modal analysis add-on to view our results here. And the first tab under the natural frequencies includes those 10 different mode shapes as well. So we can kind of cycle through these by clicking in the table, and notice the graphics will automatically update. But this allows us to view the angular frequency, the natural frequency, and the natural period of our structure for those 10 different modes. Now, it's really important to also take a look at the effective modal masses. And within this is going to show us our mass participation for each mode shape. Well, we can immediately tell what our dominant modes are here, just based on the most mass participation. So mode shape 1 would be our dominant mode in the Y direction. And we can also view mode shape 3 here, which would be our dominant mode in the X direction. And down at the bottom of this table, we will actually get a summation here of the mass participation. So in the X direction, we have 72%, and in the Y direction, we have 89%. Well, if we refer to the NBC commentary, and currently only the 2015 is released, we don't have access yet to the 2020, but I would imagine it would say the same thing, in that a 90% mass participation is required for this modal analysis. And we're certainly not reaching that with these 10 different mode shapes here. So the question might be, well, what steps can we take in order to ensure that we're meeting that 90%? The obvious and most easy is probably just to solve for more eigenvalues. Maybe we set this to 20 or 30 in order to see at least that 90% in both orthogonal directions. Alternatively, if we take a look here at mode shape number 4, for example, you'll notice that really not much is going on with a majority of the structure. Rather, we're seeing a response up here for these smaller steel members only. Same concept with mode shape number 5 and mode shape number 6. So we term these usually as local modes, where again, not much mass participation, but we're seeing very little response for just maybe a few members. So I'd really like to eliminate these local modes in my calculation. And we're going to go back to the modal analysis here and revisit these settings. Under the Settings tab, remember we have this currently set to no neglection, but what I would like to modify this to is to user defined, where I now have an additional third tab here to neglect masses of a particular object that I select within this dropdown. And for today, I'm going to deactivate the masses for all of my steel members located at that top level. And I can graphically select the steel members here. I'll turn off my results. Maybe I turn this into a rendered view by graphically using my selection box here to highlight all of the steel members. Now notice the member numbers are automatically populated. So now we're going to completely neglect the masses for those particular elements. But if we would still like to consider the masses and maybe just redistribute to a different area of the structure, we can do so. So if I highlight all of these same members, again, these steel elements up at the top, I can right click to take advantage of this option here called center of gravity and information about selected objects. And what you will notice is that the program will give me the total mass here of the selected objects, 3.075 tons. Well, I can take this a step further to generate a new node at the center of gravity with the selected objects, and we see that generated here in the background. So once I've created that additional node, I'm actually going to double click on it because I want to modify the Z elevation here to 21 meters. And by doing so, I just have simply moved this node to the top story here of the concrete structure itself. Well, now we are going to apply a new nodal load. So I choose my option directly up here in my quick tools up at the top. And instead of the load type set to the standard force, we do have the ability to set a mass load type. And again, taking into consideration the total mass of those selected steel objects, I'm going to simply redistribute it here at 3.075 tons. And I'm going to apply it to node number 491, or we could graphically select that node. But we do need to make sure that we are under the relevant load case here. So we want to apply that to the dead load case. So when I click OK, the program asks me to delete the results, and we turn this into a rendered view here. And now we see that mass load applied directly to that node, again, at that top slab here of our concrete structure. So we have the ability to apply mass loading as nodal loads, as we just saw, or line loads, member loads, or surface loads to be considered further within the modal analysis directly. So we jump back down here to the modal analysis. We're going to rerun this calculation, and remember now that we are completely neglecting the masses from the steel members, but rather we have now inserted in that single point mass load at the top of the concrete structure to simply redistribute the mass. And our hope is by still solving for 10 different eigenvalues that we see slightly better mass participation. So once the results are finished here, we can go ahead and zoom out to see the overall structure. We're currently looking at the modal analysis add-on and the effective modal masses tab. And we take a look at the bottom here for the summation of the mass participation. And now we have 96% in the X direction and 96% in the Y. So you can see by eliminating those local modes, we don't need to solve for more eigenvalues, but rather what we see here for mode number 4 and mode number 5 that were previously not a whole lot going on for the rest of the structure actually look quite good now with a response of the overall structure instead. Okay, so now that our modal analysis is complete, we have met those 90% mass participation requirements set forth by the NBC. We want to move forward with a response spectrum analysis. So we will go back to the navigator and the first tab here to revisit our base data dialog box. And under the add-ons, you can see that we also have the ability to activate our second add-on, response spectrum analysis. And under the standards, we're making no modifications here. We're still running that response spectrum analysis according to the NBC 2020, but I just wanted to point out all of the other international standards that we have available, including the ASCE 7, the Eurocode, and several other international standards. So we'll go ahead and click OK to get back here within the model where we will revisit our load cases and combinations dialog box. So we will create a fifth load case here, and this one is going to be called RSA for Response Spectrum Analysis Design. Within our drop-down box, we now have a third option available to us, the response spectrum analysis. Now, before I get into some of these settings here on this first tab, I'm going to go ahead and go over the additional tabs. As far as additional settings, this is actually not something that you need to worry about with a response spectrum analysis. With that dynamic add-on, it's really more relevant for a static analysis. So we'll go ahead and make no changes here. Under the response spectrum, we are interested in applying this response spectrum in the orthogonal X and Y directions. And this is just based on these global axes here in the background of the RFEM model directly. Now, of course, if we were also interested in a vertical seismic response spectrum, we would activate in the Z direction as well. The program has automatically set a response spectrum definition type here according to the NBC 2020, but we can go ahead and edit the settings within this particular definition type. So as far as generating this response spectrum, we have several options within the dropdown. The first is with a user define, where notice that you can input in directly the period, the frequency, the acceleration, and this diagram will be automatically created based on this input. Alternatively, we have the ability to consider from an accelerogram. So with the accelerogram, we can take a look at the RFEM library directly, where we have several recorded earthquake events from all the various countries, including Canada here. So we could select one of these particular accelerograms to be considered for our response spectrum analysis. Now, finally, the last option here is according to the NBC 2020, which is what we'll be moving forward with today. Now, it's very important to note here that under the spectrum type, we have two options, the elastic and the design. We'll actually touch on this at the end of the presentation today, but for now, we want to choose the design spectrum. And once we have set the spectrum type, we do need to input in several variables here, including the spectral response acceleration for the various periods. Well, I wanted to point out that if you do visit our website at delual.com, under solutions, we have here what's called the snow, wind, and seismic load maps, or in other words, our geozone tool. So you can see the various hazards that we can select at the top here. And for today, I have selected the seismic. And we also have implemented multiple standards from around the world, including the ASCE 7, of course, the NBC 2020, and all of the rest of the standards available here. So once we have selected our standard, this is also integrated with Google Maps technology in the sense that you can simply input in your project location, such as an address or perhaps a city. You can go ahead and select as well within the drop-down these several options that are needed for a response spectrum analysis, and the program will instantaneously return the correct information to you, again, based on the NBC. So maybe a little bit more efficient than what you have by flipping through maps. So certainly take a look at this GeoZone tool available on our website. So once we have this information, we would of course input it into the table here. We would also set additional factors such as the importance category. So for today, perhaps we set this to normal. We would set the site coefficients such as the site class, and today we'll set this to site class C. Then we also have the ductility related force modification factor, R sub D, and the overstrength related force modification factor, R sub O. Once all of the relevant information is input in here, we see the response spectrum diagram automatically created down here at the bottom. So we go ahead and click OK, and we want to ensure that that response spectrum is applied in both the X and the Y directions within this dropdown. The final tab here is the selection of modes. So what you'll see listed are the 10 different eigenvalues that we solve for from the modal analysis. And what's nice is that we also get a nice summary here of the mass participation in the X and Y directions. So 96% in both the X and the Y directions as as we have already taken a look at the previous results back in RFEM. Well, if we are interested in deactivating some of these mode shapes with very little mass participation, so for example, if we set this to 4%, notice that a couple of these modes are deactivated, yet we can still double check to make sure that we're still meeting this 90% requirement, and sure enough, 96% in the X and now 94% in the Y. Well, this just allows us to maybe speed up our calculation quite a bit without having to worry about some of these mode shapes that are, again, not contributing much to the mass participation of the overall structure. So in this case, modes number 8 and 10 will be unchecked here. So now that we are complete with these additional tabs up at the top, we go back to the main tab to talk about these spectral analysis settings. And again, by default, we do have a definition type set here. This will allow us to set the modal combination method for the periodic responses, and we have 3 different options available. We can take into consideration damping for the CQC rule, and we also will need to set the combination of the directional components, again with 3 different options available here. So this is a really important topic, therefore I'm going to jump back to the PowerPoint to explain this in more detail. So we'll begin first with the modal combination method, and that's that first drop down available to us. So I'm going to jump ahead here in this PowerPoint and what you would ultimately see in your result output once we do run this response spectra analysis. So remember that we're solving for 10 different mode shapes, or maybe we've deactivated a couple of those. So we're going to apply this response spectra analysis in both the X and the Y directions for all mode shapes selected. However, we need to somehow combine these so that we get a single response in the direction X and a single response in the direction Y. And within this dropdown, we choose the method of how these will be combined. The first is going to be the square root sum of the squares, the SRSS rule. And this is where we're going to combine the max results by squaring them, adding them together, and taking the square root. Of course, you'll notice that when we do this, we will lose the signage. The second option looks very similar here, but you'll notice that we have an additional coefficient epsilon that's included within this equation, and this is the correlation coefficient. The equation for epsilon is shown here, and the big difference between the CQC and the SRSS is we have the ability to consider damping. And finally, we have the absolute sum. This is just where the modal analysis is conservatively superimposed. So certainly, again, the most conservative approach. So once we have chosen the relevant method, what we will see in our result output is, again, a single response in the X and a single response in the Y. So the standard SRSS and CQC combinations, those first 2 methods that we were talking about, inevitably we're going to lose the corresponding internal forces. And what I mean by this is that if we take a look at, for example, a column's max axial force, we'll lose the corresponding moment in the results when we combine these. This is why we have an additional checkbox option right below this called the equivalent linear combination. And this will essentially give us a more realistic result as well as the correct signage. So taking a look at the square root sum of the squares, SRSS, with this option checked, we see the modified equation shown here. Very similar, we have the CQC with the linear combination checked. Again, we'll see how these formulas vary slightly from the formulas shown on the previous page without the equivalent linear combination activated. And finally, we have our final dropdown within these options for the directional component combination. Well, we now have a single response in the X and a single response in the Y, but we know that earthquake loads don't necessarily always act 100% in the X direction of our structure or 100% in the Y direction, but rather it's usually a combination of both. So the question is, well, how are we going to further combine these for our eventual design of the structure? And again, we have three different options here. The first is going to be the SRSS rule once again, where we square them, take the sum, and then take the square root. The second option, and probably the more common approach if we are designing two standards such as the NBC, is the scaled sum or the 130% rule. This is where we are going to consider these independent directions, but we're going to take 100% of the X and add it to 30% of the Y. Now, if we were also considering a vertical seismic in the Z, we would additionally add 30% in the Z. And we'll create a second result here with 30% in the X plus 100% in the Y. Now, the final option for this method is the absolute sum, and this is just simply where we are going to add 100% of the X to 100% of the Y and possibly 100% of the Z. So again, the most conservative approach there. But assuming we move forward with the 130% rule, which is exactly what the NBC calls out if we refer to Article 41881C, we should see two results further output in our results for the response spectrum analysis for exactly as we just discussed here in both orthogonal directions. Okay, so let us go back to RFEM yet again to choose the combination rule here. Just notice that when we have the CQC selected, we now have the ability to set that damping ratio here on the right-hand side. But today we'll move forward with the SRSS with the equivalent linear combination. Now, the signed results using the dominant mode, this is currently grayed out. We determined that with the way that the response spectrum analysis is carried out, there could be options or results that are unconservative if we were to apply this method here. So instead, in the near future, what we plan to do is to explore the option of exporting out the equivalent loads from the seismic response, and then we could certainly take advantage of options such as this for the signed results. But for now, you'll see that disabled. The saved results of all selected modes. Remember, we're combining all of our mode shapes in the X and Y direction according to the SRSS. This just simply allows us to view the structure's results, including deformations, internal forces for each mode shape as well. The combination of directional components, as mentioned, we will refer to the NBC to set that 130% rule. You see a checkbox activated here in the background. This just means that ultimately in our results, we will give you an envelope solution. So the max and min results for the 130% rule, but we will also consider 100% in the X and 100% in the Y in those envelope results as well. So this is checked by default. So once we have set this information under these particular settings, we want to import in the modal analysis from the load case. Well, we've only run one modal analysis for today under load case 4, but we could create multiple load cases for different modal analyses, and why this might be beneficial if we were making some experimentations with different mass combinations, neglecting masses, or whatever it may be, we would have the ability here to select a different modal analysis. And finally, we have the consider accidental torsion. So for this, we refer to the NBC Article 418.12.4 that tells us we do need to consider accidental torsion in our response spectrum analysis. And we do so by setting here 10% in both the X and the Y directions. And this is based on the building length in both of these orthogonal directions. And notice the program automatically calculates what this building length is, but if we would like to override that, we could certainly do so. But essentially, internally with our response spectrum analysis results, an additional moment will be applied at every single FE mesh point to consider those code requirements. So we are now ready to run our calculation, once again, you'll notice here that we have several input options that it's solving for load case 5 here for that response spectrum analysis. And this is just simply because we are considering all of the 10 different mode shapes, except for the 2, of course, that we deactivated, in both the X and the Y direction, applying that response spectrum analysis to each mode shape, and then combining according to the relevant settings that we just discussed within the PowerPoint. What else is new within RFEM 6? You'll notice that these are being solved simultaneously, taking advantage of the multi-core processor within your computer. Previously in RFEM 5, it would require each of these calculations to be run one by one. So now that the calculation is complete for the response spectrum analysis, we will jump yet again to our navigator here to this 4th tab where we see our results within this dropdown. And just like what we were discussing within the PowerPoint, we have all of the various results here for the individual mode shapes in both the X and the Y directions. But we also have 100% in the X, 100% in the Y. And we have the combined 130%. And finally, we have the scaled sums envelope, and this is going to be that envelope solution that includes the 130% rule, but also 100% in the X and Y. And you can see the envelope values can be activated here. Currently, we're looking at the max and min values. That's why we kind of see duplicate results here for our deformation, but we could set this to the max values only or the min values only, or keep this as both. But in addition to the global deformations of the structure, we can also view information such as the member internal forces. So perhaps I change this to the max values only, and I'll change this to wireframe view. We can view the maximum axial forces in our columns from our response spectrum analysis, or the shear forces or bending moments. Same concept here for our surfaces. We can activate the bending moments. We can also activate the color navigator over here. We can take a look at shear forces or those normal forces within the structure for those particular surfaces. Now, all this information shown graphically is also available in table format, similar to our modal analysis, but this time we jump to the spectral analysis add-on, and we can view here the results by member. So information like those internal forces for each individual member, and we can go ahead and turn off our surfaces here. Notice that everything is synced up in the background to show me exactly which member I'm currently looking at. We can export this to Microsoft Excel if we're interested in further sorting capabilities. Same concept here for the results by the surfaces as well. So a very important result interpretation from the response spectrum analysis is, of course, the topic of base shear or story shear. And previously in RFEM 5, what we needed to do in order to get this information out of the program was to typically take one of these column stacks here to make a copy of it. Then we would move it over here to the side of the structure, change the member type to something called a result beam. And the result beam would then sum up all the internal forces here for all of the selected objects. But now in RFEM 6, we actually have introduced a new add-on called the building model add-on to better organize this result output with the response spectrum analysis. So we'll go back here to our base data by right-clicking on the model name. And similar to what we saw here with our dynamic analysis add-ons, we can now activate the building model add-on. So keep in mind that RFEM is a nonlinear general FEA program. This means that yes, of course, we can model, analyze, and design buildings, but we also can model domes or silos or fabric tensile structures, or maybe it's an FEA of a steel connection. all of these different model types are possible. So what we're hoping to do here with the building model is to integrate more of those building specific features within a general FEA program. And this includes topics like diaphragms, shear walls, spandrels, and I will refer you to the webinar that I presented last month on concrete design according to the CSAA 23.3, which is on our website and our YouTube channel, where I actually go into a little bit more detail than what we have time for today with this building model add-on. But for today, we will go ahead and activate this here. And ultimately, what many other software companies are doing with two separate programs, with FEA as well as building specific, we're trying to integrate into a single program with RFEM. Now, at first glance, it appears that not much has changed when we have activated that building model add-on, but I'm actually going to right-click here in one of my folders within my navigator to collapse all of them, just so it's a little bit easier for you to see that we now have a new folder option here called building model. And what we need to define are the various building stories for our structure today. And we do so by right-clicking to create a new building story. The first story is by default automatically created here, but we do need to tell the program what's the base of this story and what's the top of the story. And we can do so by graphically selecting 2 points. So I'll scroll down to the base of the structure to select this point at the bottom. And then my second click is going to be at this first story height. And actually, let me click that again. Looks like I had toggled to a different point. So we see a total height here of 3.5 meters. Now, I want to also point out that over on the right-hand side, we have a nice table format that includes all of the information such as area, the length, the volume, the mass for all of the objects at this particular story level only. We also have the ability here to define a rigid diaphragm or a flexible diaphragm. Semi-rigid diaphragms are also currently in development and will be released at some point in the future. Now for today, we won't define any diaphragm. We're just going to keep this as a standard surfaces that we already have modeled in RFEM. We want to continue adding the additional stories by doing so with our button in the lower left-hand corner here, all the way up to story number 6. So the program automatically assumes we have the same story height of 3.5 meters at each level. If you did need to modify that, you could certainly do so. But again, all of the relevant information for this particular story will be displayed on the right. And now when we click OK, if we zoom out here and we kind of rotate the model around, notice that we have a graphical output of each story level shown, clear up to including the steel structure up at the top. So with the results from our response spectrum analysis, the only thing that we need to do here is to revisit our spectral analysis option within our first dropdown, but we now have a new result option called results by story. So I don't need to rerun the calculation. The program just automatically sums up the results that I already have. And now we see under this first tab, probably the most important information related to that response spectra analysis is our story shear presented at each level. So we're seeing the max and min shear force in both the X and the Y direction, again, output at each story. You'll also see the location of the resultant story force shown here with that red arrow. And we would probably take a look at the base of our structure to determine what that base shear is, again, from that NBC response spectrum analysis. The second tab is the inner story drifts, so we can view the drifts as well at each story level. Again, previously in RFEM 5, this information was a little bit more difficult to get out, but now in RFEM 6, with this building model output, we can directly see this based at each story level. The centers of mass and centers of rigidity are displayed here within table output under this third tab, so we can see centers of mass are actually also displayed here with these particular round circles shown here, or this mass ball at each particular level. Centers of rigidity would be available if we had rigid diaphragms defined, which we don't for this example. And the final tab is the forces and shear walls. So we can actually sum up all of the internal forces for these vertical shear walls at each story level as well. So going back to the base shear, I want to switch back over to the PowerPoint to explain the requirements from the NBC 2020 when we are talking about base shear. So let us begin with just a basic overview of some of the shear variables that are defined within the NBC. And we begin here in Article 418.12.5, where we can see that the elastic base shear from the dynamic analysis is denoted here with V sub E. So this is purely the base shear with no factors applied to it. We then have the adjusted elastic base shear in 418.12.6, and this is V sub ED. Well, this adjusted elastic base shear is actually calculated with this factor shown out here in front multiplied by the elastic base shear V sub E. And this factor isn't always applied to the structure. There are certain criteria when you should apply it to your particular building. You'll also notice that we need to take the max of the equation shown here on the left versus the equation shown here on the right, but both of them should be less than or equal to 1.0. Well, moving on in the NBC, we then have the specified lateral earthquake force from 418.12.7, V sub D. And V sub D is calculated by taking that adjusted elastic base shear and multiplying it by the variables including I sub E, which is the earthquake importance factor. And we further divide here by R sub D, which is the ductility related force modification factor multiplied by the overstrength related force modification factor. Well, now we want to back up a step, back to that simplified method, the equivalent static force procedure. And in particular, we just have the variable V that is calculated here for the lateral earthquake force from Article 418.11. So this might be something that you can easily calculate with hand calculations or some external tool that you might have. Well, if we refer to section or Article 418.12.8, this tells us that V sub D, our specified lateral earthquake force over V from that simplified method, if it's less than 0.8 or 80%, we also have the criteria here, V sub D over V. If it's less than 1.0 for irregular or timber structures set forth in 418.12.9 and 12, then we must scale V sub D to a minimum value of 80% of V, again, from that simplified method, or 100% of V if we're meeting this additional criteria set forth in the code. So the question might be, well, with all of these different base shears, what is RFEM giving me? So on this next slide, let us talk about the result output from the response spectrum analysis. If you remember, when we created that response spectrum analysis definition type according to the NBC, we had set the type to design spectrum. And with the output that we have seen up until this point in time in our RFEM example, this is actually giving us our base shear for the specified lateral earthquake force V sub D set forth in Article 418.12.7. However, I do want to clarify it does not include that additional factor from 418.12.6. Again, there is just specific criteria on when that factor needs to be applied versus when it should not be applied. So we have left that up to the user. However, it does include the factor I sub B over RDRO from 418.12.7. So this is ultimately the information that we're getting in the base shear building model add-on results with the design spectrum type. If you also remember, I had mentioned there is the elastic spectrum type that we haven't seen so far, but that is the additional option within the dropdown. This is going to give us the elastic base shear, V sub E from 41812.5. So it includes no factors at all, including that I sub E over RD times RO. And we might use the elastic spectrum to take a look at the lateral deflections of our structure set forth by the NBC from 418.13.2. And if we refer to the NBC in this particular criteria, we really need to limit our drifts set forth by the code. Again, we would do so with that elastic spectrum type. Now the question might be, well, what if I would like to include this factor in my design spectrum? Or on the previous slide, what if I need to scale up my base shear? How can I consider that with the RFEM options? And if you remember, I briefly touched on the scale factor that is available here. So we can, by default, the program has set this to 1.0, but we can adjust this if we would like to consider this additional factor for the design spectrum, or if we needed to scale up the story shear force or the base shear force. So let us go back to RFEM here, and I'll quickly show you how we can consider that elastic design spectrum. So going to our load cases and combinations, I'm going to make a complete copy of load case 5 here. And instead of my response spectrum analysis for design, I'm going to rename this to elastic. Now, all of the previous settings are also copied over, so I don't need to make any modifications to this. But under the response spectrum type, I'm going to edit the definition type here to also create an exact copy of my existing response spectrum definition. And up at the top, I'm going to modify this to elastic. Now notice that a lot of the input criteria is now gone, and that's again because we're not considering those additional factors here with our response spectrum analysis with the type elastic. So now that we have this second definition type here for elastic, I can simply select it in my drop-down box. And we would rerun the calculation. We would take a look at the building model results, and in particular, the drift, to make sure that our drift is limited to what Article 418.13 has set forth. No need to run that calculation now. It's really the exact same workflow. I just wanted to show you how we can essentially consider that elastic response spectrum analysis. Now, the final topic to cover is we now have our earthquake loads from this design response spectrum. How do we combine this with the other load cases such as dead live snow, or perhaps we have additional lateral loads like wind analysis? So if I go back to my base data, we probably would carry out the design here utilizing the concrete design add-on or the steel design add-on. Notice we have timber for CLT structures, aluminum, we have cold form steel, whatever it may be. And under the third tab now, we get some additional options to carry out this design specific to the CSA standards for both concrete and steel. Now, again, I have previous webinars that are dedicated to these particular topics. So you can refer to those on our webinar and YouTube channel within our website. But for today, I just want to briefly show that we would probably, again, carry out the design of our structure utilizing these design add-ons. Well, if we go back to the load cases and combinations, and we take a look at here the design situations. Again, I had mentioned that the program will automatically create these two design situations, and we'll go ahead and activate them again for the ultimate limit state and serviceability limit state that we'll eventually use within the concrete and steel design add-ons. That's why they're both checked here. If we take a look at the load combinations that are generated from these two design situations, you'll see here that I don't see earthquake listed at all. And the reason why is because these load combinations are being generated according to a nonlinear second order analysis to consider those P delta effects. But we know that we cannot simply add the earthquake loads to these additional load cases using superposition, because we can't combine second order effects and just add them together like P delta. So instead, we want to come in here for the ultimate limit state and go ahead and edit these settings here. Again, the default is set to second order analysis, but we're going to create a new definition type. And instead, we want to combine these earthquake results in a linear analysis using result combinations. So once we have selected this new definition type, we want to additionally select it here within our drop-down box for that ultimate limit state. And now we get a new tab called result combinations. And sure enough, we see here dead, live, and snow, but we also see that earthquake load listed here from our response spectra analysis and the design. Notice also the sub-results. Currently, the scaled sums envelope will again reference the envelope solution from the 130% rule, 100% in the X, 100% in the Y. But if we wanted to consider one of these other scenarios, we could do so within the dropdown. But the default scaled sums envelope will take the max and min results here for this result combination. We also see a second result combination with our elastic response spectrum analysis. And for this, we actually refer back to the NBC commentary 2015, and in particular, Appendix J, Note 111. And the commentary tells us that earthquake loads are considered rare. So there are no general requirements for SLS design when considering earthquake. Rather, we take a look at the specific elastic response spectrum analysis to make sure that our drifts, in particular under only earthquake loads, are limited according to what the code has set. Therefore, I really don't need to include this in my load combinations as well. So I certainly could go back to the result combination and just uncheck the solve, but probably the better option under actions is you'll see here a separate action category assigned to my response spectrum for the elastic type. I can uncheck the active here. And now under my result combinations, we only have a single result combination considering that design response spectrum analysis. When it comes to SLS design, we see here our design situation for SLS design. This is set according to second order. That's probably fine because we are able to combine now for our load combinations for SLS for dead, live, and snow. But again, for the ultimate limit state or ULS design, we can't do so with a response spectrum analysis. We must combine them linearly. Okay, so that will conclude our presentation today. This webinar was recorded and will be up on our website usually within the next day. The model used in the presentation is available on that same web page that you have registered for the webinar, so you can download it. You can also download the 90-day trial version of RFEM 6. So all of the add-ons that you saw today, including the rest that you haven't seen, will all be full capability for the full 90-day duration if you'd like to take a look and kind of test out on your own projects. If you have any questions about today's presentation or any of our products, feel free to contact our Philadelphia office with the contact information shown down here at the bottom. Our phone number is 267-702-2815, and our email is info-us@duluval.com. So we will have more upcoming webinars presented approximately once a month that you can register at duluval.com under support and learning webinars. As most of you know, I will send out a reminder email about a week before these take place. So feel free to register directly through the email and keep an eye out for that within the upcoming month. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So that is a requirement of the states that we are pre-approved providers, that if you do want that PDH, you must be here for the full 60 minutes. If you did watch with a colleague or you watched in a conference type setting and you yourself did not register with your own name and your own email and you were here for the full duration of the webinar and would like PDH, please request that at the email address shown here, info-us@delual.com. Again, if you yourself did not register with your own credentials, you were here for the full presentation, just let us know who you watched it with and we'll be happy to generate that PDH certificate for you. I should also note that this is not instantaneous. As soon as the webinar ends, it's usually sent shortly after, within the day at the most, for when you can expect to receive that email. And with that said, I want to thank everyone for attending, and as always, we hope to see you at our next presentation. Thank you.